lab like a screw jack. So you give through the handle, you give rotation. So the screw will start moving up along with the weight over there. So that means this weight has got linear motion for the revolutionary motion that you give at the end of the handle. Is that okay? Right. So this is what again. So this is another type. This is the worm. This is the threaded fastener, and then this is the worm gear. That what you see inside is called worm gear. This is worm shaft. Okay. There is a thread. So a power screw is a device that's common to tools or machinery and used to change angular motion into translation or linear motion. Right. And also it is capable of developing large amount of mechanical advantage. Examples include, as I said, clamps and vices, bench vise that you have seen, where you give rotation to the lever, the jaws will move in a linear direction. Okay. Then presses lathes of lathe lead screws that you would have seen, tool post, right? The tool post, as you give revolution to your hand wheel there in the for the tool post, it will move linearly. So beneath that you will have a lead screw. Okay. And then, as I said, another example is screw jacks that we have seen in normal operations, where you give revolutionary motion, it will lift the car up. So that's a linear motion. So rotational motion is converted into linear motion. That is the job of a power screw. Are you all there with me? Are you all there? Yeah. Can anyone say yes?
Yes, sir.
Yes, sir.
Yes.
Yeah, what you do is, please note down this definition into your notebook. And this is sketch. This sketch you note down. The definition and the sketch you please note down into your notebook. If you are finished, let me know.
Excuse me, sir.
Yeah.
Sir, what do you mean by mechanical advantage?
That's the generally you can take it as the input to the output ratio. Okay. You have learnt about the levers, no? You have learnt about levers. Okay. So you have a
Yes.
lever. So the point where you apply the pivot point that you have got. Okay, so you apply lesser force, you will get more output. Okay, for 10 kg input, you may get, depending upon the lever ratio, you will get more output. That is the mechanical advantage.
Okay, sir.
Yeah. Say, for example, if you do you have a car? Do you ride car? Do you drive car?
No, sir, I don't drive.
Um, a bike you have drive, you have ride it, bike you have rode.
Yes. Yes, sir.
Yeah.
Yes, sir.
So the brake pressure that you apply on the foot, no, it will be hardly around, I would say some 200 Newton or not 200 Newton. Sorry, it's not even 1 kg. Okay. So it is not even 1 kg into, how do you convert Newton into Newton? M into G. Okay. Right now. So you apply hardly around 1. Yeah, are we connected?
Yes, sir.
Yes,
Yeah,
sir.
yes. Yeah, who asked the question? I was explaining, but in between there was no connection.
Yes, sir. That was me, sir.
Yeah, so so basically, where did I stop actually?
Sir, you were telling about the point where we put the pressure on the pedal of a bike.
Yeah, of a bike when you apply, it's hard, not even a kg of load that you apply on the bike brake pedal, but at the brake drum, it will be almost 5 to 8 times because of linkage ratio. So that's the load that is realized at the brake drum. Similarly, when you look at the screw jack, no, I mean screw jack or yeah, screw jack that we use for car lifting, right? So lifting of car for changing the tires and so on. The car, if you take a small car, which is around 1000 kg, is the weight of that car. So it is taken to have 250 kg each at each of the wheels. That is, 250 kg is distributed, each wheel will take up the load. Okay. So
Yes,
the
sir.
screw jack that we use, we hardly apply 4 to 5 kgs of load for the screw jack. Okay. But the lift that we get is around 250 kg load, it will lift. Okay. So for 5
Yes,
kg load that we apply, it's able to lift a load of 250 kg. Okay. So that is the mechanical advantage we talk about. Okay.
yes, sir.
So
Yes, sir.
the
Thank you.
ratio between input and output is the mechanical advantage that we get. Okay.
Yes, sir.
Yeah. Yeah. Have you all noted down, completed noting down this? Yeah.
Yes, sir.
Yeah. Can you see? Can you see this bolt and nut that I am holding on in my hand? Can you see?
Yes, sir.
Right. So this again rotary motion to translatory motion or translation, I would say. So this is the nut and bolt arrangement. These are the threads. Okay. Power screws or screws is what we are going to learn about. So now to this, I am going to give rotary motion. So what's happening to the top of the bolt is it is having linear motion. That is why it is going up in linear direction. Whereas the motion, the rotation that I am giving is a rotary motion, but the screw that is traveling up will have linear motion. If I place a load on this, then what will happen? It can lift up, that is, it will have linear motion, right? That's the job of power screw. Is that okay? Is that fine?
Yes, sir.
Have you noted down this sketch? Have you noted down the sketch? Yeah, noted or not noted?
Yes, sir.
Noted down the sketch?
Yes, sir.
Someone should say quickly, okay? Otherwise, yeah. And then we have learned various types of threads in our machine drawing class. Have you done this? Have you learned?
Yes, sir.
Have you drawn this
Yes.
in machine drawing? Did you had the type of threads drawing in machine drawing?
Yes, sir.
Yes, sir.
Right. Right. So these are some of the various types of threads depending upon the application. So we have buttress thread, we have square threads, which is used in screw jacks. Acme threads are trapezoidal threads, which has got an angle 2 theta. The angle of threads is 2 theta. That's around 29 degrees. Pitch is the distance between two crests or roots. This is what we have learned. We have got 60-degree stub. We have got unified threads, Whitworth threads, and so on. All these have come into picture depending upon the type of application. Knuckle threads, if you see, they are used in recirculating ball screw assembly. So like that, we have, depending upon the type of application, various threads have come into picture. Now, this is what, again, to understand terminology of threads again that we have learned. This is the major diameter, right? Major diameter denoted by D, which is the largest diameter of a screw thread. Okay? And the minor diameter is the smallest diameter of the screw thread, and it is also called as core diameter denoted by D1. Major diameter is denoted by D. And there is one more thing called as pitch diameter, which is at the pitch circle of each of the threads. That's called pitch diameter or mean diameter denoted by D2. And the depth of thread is nothing but the difference between major diameter and minor diameter will give you the depth of thread. And what is pitch? What is pitch? Pitch is the distance between any two crests or any two troughs. What is a crest and what is a trough? Let's see that. Or root, right? So these are the crests. The peak points are called crest and the deep point is called the root. So the pitch is the difference between two crests or two roots, right? Between two roots, something like this. Okay, that is crest and root in case of a thread terminology. Again, we are showing here major diameter D, minor diameter or core diameter D2, and pitch diameter. Okay, pitch diameter. What is that we have taken for pitch diameter? Mean D2. Okay, minor diameter is D1. Okay, and the angle between two flanks is called the thread angle. Next, again, Same thing over here with little more root, crest, pitch, okay? Major diameter, pitch diameter or mean diameter, minor diameter or core diameter, okay? D1. Please note down into your notebook this sketch and the conventions. Please note down this. Please note down all the terms. Write down the sketch into your notebook. Write down the terms. Don't just keep quiet. Okay, switching on the mobile. So it will not help you. Please take notebook, pen, write down the diagram, and then note down all the terms. Okay, then only we will be able to design and understand the power screws. Is that okay? Please note it down. Answer your roll call in the meantime. 1,
Present.
2,
Present, sir.
3, 4, 5, 6.
Present, sir.
What, Anwar, where were you for last 5 classes?
Sir, I was not feeling well, sir.
Okay. Akshay Jadhav, Alap Mundior,
Present, sir.
9, 10,
Present, sir.
11, Biban Kalita, 12,
Present, sir.
13, 14,
Present, sir.
15.
Present, sir.
So Charishma present.
Yeah. Taken, Charishma. 17,
Yes, sir.
Ibab Kausar. 18, 19, 20, 21,
Present, sir.
22,
Present, sir.
23,
Yes, sir.
24, 25, 26, 27, 30, 31, 32, 33,
Present, sir.
34,
Yes, sir.
35, 36, 38, 39, 40,
Yes, sir.
41, 42.
Yes, sir.
Yes, sir.
Hey, what is the double voice coming? 41 is present. 41,
Yes, sir. 41 present. Yes, sir.
42,
Yes, sir.
okay. 43, Rakshit. 44,
Present, sir.
45, 46, 47,
Yes, sir.
48,
Yes, sir.
49, 50,
Yes, sir.
52, 53,
Yes, sir.
54,
Yes, sir. Present.
55, 56,
Present, sir.
57, 58, 59, 60? Yeah. 61?
60 Tarun is present, sir. His mic is not working.
Who is that? Siddharth Sanu, is it?
Tarun, sir, 60.
60. Tarun, okay, Tarun, got taken. Yeah. 61? 62?
Yes, sir.
63? 64? 65?
65 present.
Okay. 66?
Present, sir.
67? Chaitanya? Chaitanya? Mahesh? Nishant? Ramesh? Shashank?
Yes, sir.
Akshat?
Present, sir.
Sautrik Roy?
Present, sir.
Mahima Raj?
Present, sir.
Srivatsan?
Present, sir. Present.
Okay. Suman Xavier? Madan Kumar? Manu? Shadab? Ganesh? Vijay Kumar?
Sir, Ganesh present, sir.
Ganesh present. Vijay Kumar? Rishi, yes.
Yes, sir.
Zair Hussain?
Oh, 76 present, sir.
Yeah. So this is the terminology of screw threads I think you have taken. Okay. Next, let's understand what each term is. Pitch, it is the distance between two adjacent crests or root, okay, measured parallel to the axis of the thread, right? This is the pitch of the thread either between two crests or two roots like this, something like this, okay? So this is the pitch. Major diameter, as I said, it is the largest diameter of the screw thread. It is also called basic diameter or nominal diameter, denoted by D. Minor diameter or core diameter, D1. It is the smallest diameter of the screw thread. It is also called core diameter. For practical purposes, we are going to take D1 to be equal to 0.8 times D. Then pitch diameter or mean diameter is nothing but D plus D1 divided by 2. Okay, that is this minor diameter, major diameter plus minor diameter divided by 2 will give us the mean diameter or pitch diameter. Then lead, okay, it is the axial distance covered by a nut. Say for example, when you take out a nut, okay, this is the cross section of the thread that we are going to get. Okay, right, this is the lead. This lambda or alpha is called the lead angle or helix angle, and this distance is called the lead. So when you have that lead, right, what does that lead is all about is nothing but when you give one rotation, okay, say suppose I have a screw thread something like this, right? So the when I give rotation to this one rotation, if I give, this will travel axially by some distance. So that axial distance covered by the nut along the length of the screw when it is given one rotation, that is, if you look at here, so I'm holding this, I am going to give one rotation to this. Okay, one rotation to this. When I give one rotation to this, the axial distance covered here is called the lead of the screw. Along the length, what is the distance covered is what we call it as the lead. Are you all getting it? So now I am having this, I'll give one rotation to this. The axial distance covered by this per screw or length along the length of the screw is called the lead. Is it okay? Is it okay? And if you look at here, the pitch is distance between two threads. Okay. So when I give one rotation, axial distance traveled by the length of the screw is called the lead, or in definition, axial distance covered by a nut along the length of the screw when it is given one rotation. Is that okay? That is lead. That's very, very important term in designing of power screws. Are you there with me? Are you there?
Yes, sir.
Yeah. Please note down. Please note down pitch, major diameter, all the definitions. You please note down. Okay. Because for entire 2, 3 chapters, 2, 3 topics, we should have clarity of all these things. So please note down what definitions of each of them. Note down this. And let me know once you have completed. Please take notebook and write down, okay? Finished, huh?
So 1 minute.
Yeah. Yeah. Is it there now? There was a connection disturbance. Are you people there?
Yes. Yes, sir.
Did you finish writing down this?
Yes, sir.
Okay. Next. Yeah. Are you all there? Are you all there?
Yes, sir.
Right. So this is what we are trying to understand the thread terminology over here. I take a single thread, okay? I take a single thread. This lambda or alpha is called lead angle, and this L represents height of each thread, that is called lead, and the force F will be acting downward on the thread like this. I have taken one single thread and I am trying to analyze. Okay, so the angle alpha is nothing but the lead angle. Opposite side is called the lead. That will give you the height of the pitch over there. And then F is the load that is acting on the screw thread, right? So the N represents normal reaction force, and this distance will give you circumference of the thread along its pitch diameter, denoted pi dm, or in our case it is called pi d2, which is the circumference of the pitch diameter. F is the applied load or weight to be lifted, and N is normal reaction force, and Fn is the coefficient of thread friction that is coming over here between the load applied and the threads that is there. So between the metal to metal, we have got what is called as the friction. Okay. So what are the things? We have mean the circumference of mean diameter. F or W is the load that is acting. N represents normal reaction force for the applied load, and small f or mu represents okay, coefficient of thread friction. Are you with me? Are you with me? Yeah.
Yes, sir.
Okay. So now coming back to this. So for a single start thread, we have lead is equal to pitch. What is lead? Lead is the axial distance traveled when by the nut along the length of the screw when one rotation is given. Okay. So lead will be equal to pitch for a single start thread. Right, lead is equal to pitch for a single start thread. That is, if I give one revolution, the nut will travel along the screw equal to its pitch. That is, L is equal to pitch in case of single start thread. In case of double start thread, it will travel 2 times the pitch for every one rotation that is given, right? And similarly for a triple start thread, it will travel 3 times the pitch length, okay, for every rotation that is given. Is that okay? And what are flanks? They are the sloping sides. They are the sloping sides of the thread called the flanks. And the angle between 2 adjacent flanks of a thread is called thread angle. And for trapezoidal or acme threads, the angle of our thread angle is 2 theta, that's given by 29 degrees. And the understanding of a square thread is that if it is represented as SQ40 by 7, that means that it's a square thread of 40 mm nominal diameter and a pitch of 7 millimeter. This is the designation of a square thread. Okay. For a metric thread, it will be preambled by the letter M, indicating that it is a metric screw thread, followed by the nominal size and pitch separated by an into mark. That is, if we take M20 by 2, it is a metric screw with 20 mm nominal diameter and has got a pitch of 2 millimeter. If it is to be, if length of the screw is also to be included or indicated, we can have something like M20 by 2 by 40. M stands for metric thread, 20 stands for nominal diameter, 2 stands for pitch, and 40 stands for length of the screw thread. Is that okay? These are certain terms that are required to be known to us before we get into the design. So first what you do is note down the sketch. Note down the sketch first. Note down this much. Note on this. Where lambda or alpha is called lead angle or helix angle of a screw thread, L is the lead, pi into dm represents circumference of the pitch diameter given by pi dm, or in our case it is called pi d2. F is the applied axial compressive load on the screw, F or W. You can use, normally we use W in our case, and F stands for, smallest stands for the coefficient of thread friction, either small f or mu. Please note down the sketch. Once you have finished, let me know.
Done, sir.
Yeah.
So 1 minute, sir.
Here, if you look at lead angle or helix angle, which is tan alpha is equal to opposite by adjacent, that is L by pi into D2, where L is equal to lead and L is equal to P for single start thread, and L is equal to 2P for what type of start? Double start thread, and length lead is equal to 3 times the pitch for a triple start thread. So when you are asked to design a triple start thread, when you are calculating tan alpha or lead angle over here, alpha, so in place of L, if it is for triple start, so we need to take 3 times the pitch divided by pi d2 will give you the value of tan alpha, that is nothing but the lead angle or helix angle of the thread. Okay, if you miss out on 3, then your entire design is taken to be wrong. Okay,
Done, sir.
yeah. Come back to this. So please note down, for a single start thread, lead is equal to pitch. For double start thread, lead is equal to 2p. For triple start thread, lead is equal to 3p. And note down what is flank. Sloping sides of thread are called thread flanks or flanks. Thread angle is the angle between two adjacent flanks of a thread is called thread angle, and square thread representation and metric screw thread representation is M20 by 2. So please note down these few lines into your notebook. Please note down these things into your notebook and go through. Okay, please note down these.
Done, sir.
Yeah. Okay. So this one have you taken? D1 is equal to D minus P. D2
Yes,
is
sir.
equal to, yeah, this you have taken. Okay. Now, again, coming to, I was talking about the coefficient of thread friction that is denoted by F or mu is coefficient of thread friction. So it depends on the type of lubricant, of course. So whenever you have got moving parts, right, then we will be using lubricant to take away the temperature and also to reduce the wear and tear of the components. We use lubrication. Okay. So depending upon if we use machine oil or graphite, we can take coefficient of friction is equal to 0.17. Normally lard oil is used. Okay, so we take F is equal to F or mu is 0.11. For heavy machine oil, we take mu is equal to 0.14. And then regarding collar friction, we'll take up in the next class. Please note down this. So the coefficient of friction, thread friction, depends on the type of lubricant. So therefore, F is equal to or mu is equal to 0.17 for machine oil, and F is equal to 0.11 for lard oil, F is equal to 0.14 for heavy machine oil. Please note down this much. F or mu represents coefficient of thread friction. So, and the coefficient of friction, thread friction depends on the type of lubricant that we use. So we take 0.17 if we are using graphite, we'll be using 0.11 as coefficient of thread friction if we are using lard oil. And if we are going to take F is equal to or mu is equal to 0.14 for heavy machine oil, for time being you just note down coefficient of collar friction, we take it as 0.17 normally. Okay, please note down this much. Please note down this much. So in our data handbook that we use F as the coefficient of friction, FC as coefficient of collar friction. Please go through whatever that is done today before you come to the next class. Okay? Because all these terms, what is D2, what is D1, what is D, what is P, all these things should be there in your mind. Okay, before we start with the design of square threaded fasteners, then angular square thread screws, and so on. Anyway, topic will be easy. Only thing is you should have clarity of these major diameter, minor diameter, mean diameter, and so on. Okay? Finished?
Yes, sir. Done.
Yeah. So tomorrow before you come for next class, okay, please go through